Hi everyone. In this video, we're going to talk about the comparison test. The idea behind the comparison test is similar to that of the squeeze theorem. What we're going to do is try to compare a given series that has positive terms to a known series to determine if our series converges. So, since we're going to need comparison series, now is probably a good time to recall some series that we have in our toolbox. The two types of series that will be especially useful as comparison series are p-series, which we talked about in the last video, and geometric series. The great thing about these series is that it's super easy to tell if they converge or diverge. We'll see how this is helpful in just a second. But first, let's actually state how the comparison test works. The comparison test says, suppose we have two series, the sum of an and the sum of bn, where all of the an's and the bn's are positive numbers. Then there are two statements. First, if the sum of the bn's is convergent and bn is bigger than an for all n, then the sum of the an's is also convergent. On the other hand, if the sum of the an's is divergent and the bn's are still bigger than the an's for all n, then the sum of the bn's is divergent. Intuitively, it may be helpful to think about it like this. Say we have two series that have positive terms, and one is bigger than the other. If the bigger series converges, then that squeezes the smaller series into converging as well. However, if the smaller one diverges, then that's going to push the bigger one into diverging also. Let's see how this works in some examples. Suppose we have the sum from n equals 1 to infinity of 2 to the minus 1 over n cubed. Now, we have two choices. Either we can find a larger series that converges, or we can find a smaller series that diverges. To help make this choice, we should analyze the terms of our series. We see that the numerator goes to 1 as n goes to infinity, and the bottom goes off to infinity. So, it appears that the bottom is the more significant part of the series. In other words, it seems like this series should behave like the sum of 1 over n cubed, which is a p-series with p is equal to 3, and so it converges. Therefore, our guess is going to be that the series converges. So, let's try to find a bigger series that we know converges. What we can do is rewrite the 2 to the minus 1 over n cubed as 1 over n cubed times 2 to the 1 over n. I always like to try and get rid of negative exponents because they're just kind of confusing. And now, as a general rule, the most common way we're going to find comparison series is just by kind of dropping off things and seeing what happens. In this particular example, we can just drop off the 2 to the 1 over n in the denominator and get 1 over n cubed. And since 2 to the 1 over n is greater than 1, this has the effect of making the denominator smaller, which in turn makes the entire number bigger. Therefore, we found a series that is larger than the series we were given. Moreover, we know that this series converges since it's a p-series with p is equal to 3. Thus, by the comparison test, our series converges. For the next example, consider the sum from n equals 1 to infinity of 2 to the 1 over n. Again, we see that the top goes to 1 and the bottom goes off to infinity. So the bottom should be the more significant part. And this series should behave something like the sum of 1 over n, which is the harmonic series, and we know that this series diverges by the p-series test. Therefore, our guess is going to be that this series diverges. So, our job is now to find a smaller series that we know diverges. It actually turns out to be a little simpler in this case. Since 2 to the 1 over n is bigger than 1, we have that 2 to the 1 over n is bigger than 1 over n. And then, just like we said before, the sum from n equals 1 to infinity of 1 over n diverges by the p-series test. And so we have a smaller series that diverges, and so the original series must diverge as well. Next, let's look at the sum from n equals 1 to infinity of 1 over n squared plus 1. The first thing we need to do is decide if we want to show that the series converges or diverges. Well, the most significant term on the top is 1, and the most significant term on the bottom is the n squared. So, this series should behave something like the sum of 1 over n squared, which is a convergent p-series. So, we're going to guess that this series converges, and now we must try to find a bigger series that also converges. Our strategy here is again going to be to just drop off insignificant terms to make the series look a little bit simpler. Let's take our 1 over n squared plus 1 and drop off the 1 in the denominator, and we're left with 1 over n squared. Since dropping off the 1 makes the denominator smaller, this will make the entire number larger. Also, just like we mentioned before, the sum of 1 over n squared is convergent by the p-series test. And so, we've found a bigger series that converges, and so the original series has to converge as well. Now, I don't know if there's such a thing as too many examples, so let's go ahead and try one more. Consider the sum from n equals 1 to infinity of n to the minus 2 over 2 to the n. Again, I don't really like dealing with negative exponents, so let's rewrite this as 1 over n squared times 2 to the n. And now we need to guess whether the series converges or diverges. Here, I'd like to point out a general rule of thumb, which is that exponentials are always more significant than polynomials. I should be a little careful here and mention that I'm talking about exponentials with a base that's bigger than 1. So, for example, 2, just like we see here. The point is that this series should behave something like the sum of 1 over 2 to the n, which is a convergent geometric series. So, our guess is that the series converges, and so we need to find a bigger series that also converges. Just like before, we can do this by dropping off the n squared in the denominator to get 1 over 2 to the n. And since n squared is bigger than 1, this will make the denominator smaller, and so the whole fraction becomes bigger. Furthermore, we know that the sum of 1 over 2 to the n converges by the geometric series test, and so our original series must converge as well. Alright everyone, that's all I have for you this time, and have a great rest of your day.